Hello everybody, Adam Lusek here, and today we're going to be talking about reinforcement learning with large language models. Reinforcement learning already plays a big part in the post-training of language models, but recently over the last few months has gained a lot of popularity and traction as it's been shown to be useful not just for the alignment of language models, but also for generalizing procedures. So I thought now would be a good time to put together some resources around the context of where reinforcement learning has been applied to language models in the past, how it's being applied now, what makes it different, and why this is important. So today we'll be covering the background and theory of how reinforcement learning has been traditionally applied, how that's led to using reinforcement learning with verifiable rewards and creating reinforcement learning environments for these kinds of scenarios, the benefits of using reinforcement learning with verifiable rewards, and then of course, how to put it all together to train a language model using all of these new techniques. And putting this resource together has been exceptionally interesting because reinforcement learning in particular really parallels a lot of how we as humans tend to learn. We'll tackle problems iteratively, often trying multiple different solutions to a problem at a time, seeing what works, what doesn't work, and adjusting our behavior based on that. And this process isn't just something that a language model can take advantage of, but also something that you yourself can actually do, which is especially true if you're using the right tools, like the sponsor of today's video, Brilliant. Brilliant helps you become a better thinker and problem solver with thousands of visual, interactive lessons in math, science, programming, data analysis, and artificial intelligence. Crafted by an award-winning team of teachers and researchers from places like Stanford, Microsoft, Caltech, and Google, Brilliant is a learning app designed to be uniquely effective. Each lesson is filled with direct, hands-on problem solving that lets you actually play with the concepts, a method proven to be 6 times more effective than traditional lecture videos. Brilliant helps you build understanding from the ground up through a perfect mix of engaging problems and competitive features, not just memorizing the content. Brilliant's growing collection of programming, data science, and artificial intelligence courses are a great way to build timeless problem-solving skills to thrive in an evolving world. You'll get hands-on experience with real programs, use real-world data from places like Airbnb and Spotify, and become a better thinker and problem solver all at once. To learn for free on Brilliant, go to brilliant.org/AdamLusek, scan the QR code on screen, or click on the link in the description. Brilliant's also given our viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. Now back to the video. When you consider the life cycle of creating a language model, much of actually learning the language and the representation of language comes from the pre-training phase. This is then harnessed, aligned, and improved through multiple rounds of post-training and fine-tuning. Within the post-training phase, we tend to rely on 3 main techniques for actually aligning and getting those quality and expected responses. That is using supervised fine-tuning, preference training, and different reinforcement learning approaches. There's generally not one strict order for all of this, but these are used in different times through the model's training lifecycle, and depending on what goal you are trying to get out of the model. But in order, we tend to see that training a language model follows this 4-step process of doing the pre-training, then some sort of supervised fine-tuning, and then a mixture of preference training and targeted reinforcement learning. Pre-training is going to do what we expect of teaching the language model about language and the world in which it lives in. Supervised fine-tuning is then used for things like instruction following, different formatting rules, and also tool use. We then use preference training to push general answer quality and safety higher, so getting it more aligned with outputs that humans actually prefer. And then targeted reinforcement learning is where we apply things with strong rewards like coding, math, and tool use to generalize our procedures. Then, depending on what the goals and capabilities required are, there's usually some form of refresh and mixing and matching of all of these 3 techniques to get the desired result and behavior out of the model. Reinforcement learning itself is then used in the preference training and, of course, targeted reinforcement learning stages here. In the past few years, we've seen reinforcement learning from human feedback play a big part in the actual alignment and preference training of language models. But more recently, reinforcement learning with verifiable rewards has led to things like DeepSeek R1's emergent reasoning capabilities and offer all sorts of other benefits for procedural generalization. But before we go deeper into that, let's start with a quick refresher of language models and reinforcement learning. At a high level, reinforcement learning trains an agent, which in this case refers to the large language model, and as a note, is not to be confused with the modern definition of a language model agent, which is a language model running in a loop with tool calls. Rather, this is referring more towards what is actually acting within the reinforcement learning environment. So, the agent in this case interacts with an environment, which is the task context, by taking some form of action that maximizes a cumulative reward over time. And the objective of reinforcement learning is to learn a policy that achieves the highest expected total reward. Now, to break down what some of those specific means, the policy in this case is actually the language model itself, which in our scenario generates a sequence of tokens in response to a prompt. Now, these tokens can represent either the tokens themselves, or they can be aggregated to constitute the generated text, or complex behaviors such as function calls, tools, or other actions, especially in things like agentic scenarios. And all of these actions happen within a defined environment. Now, the environment itself is super important because this is what provides the context within which the model generates. It's essentially the world that the language model lives in and does its actions within. And when a model does perform an action within the environment will return back some form of feedback based on what has happened. And this feedback is what we refer to as a reward. Rewards are then either positive when desired actions are taken, or negative when unwanted actions are taken. These positive and negative signals are then all processed via reinforcement learning algorithms to then adjust the policy of the language model to maximize the cumulative reward over time, or essentially encourage the desired behavior. If you look at my incredibly abstract interpretation of this in a diagram, you might consider a reinforcement learning environment with a language model in process being a series of prompts, one by one being fed into a language model, where the language model then takes some form of action, which can be just generating a token, generating multiple tokens, generating multiple sequences of tokens, doing some representative thing with those, like taking a tool call or a separate outside action, and this all happens within the environment. Based on those actions and our defined reward values and reward functions, a reward is calculated, which is then used to train and update the policy of the language model to further guide it towards doing the desired things and away from the undesired things. And as mentioned, this is applied to language model training in a few ways, but before any reinforcement learning is actually even applied, a base pre-trained language model typically undergoes some form of supervised fine-tuning on curated input and output pairs. I would say that supervised fine-tuning is what most people think of when they think of fine-tuning language models, and can best be thought of as imitation learning. It's considered this because it essentially trains on perfect examples of what we expect an input and output to be. This is useful for a few reasons. First, it can help make the model consistently follow instructions and different expected formats. It can set tone, safety, and refusal patterns, and also teach basic tool use and multi-turn etiquette through golden examples here. In the end, it also helps us establish a reliable reference policy that we can then apply further reinforcement learning to. But its limitation is that supervised fine-tuning is very effective for teaching behaviors and injecting domain knowledge, but it doesn't directly optimize for global outcomes, which is where reinforcement learning actually comes into play. Initially, reinforcement learning gained popularity through post-training strategies for what we call alignment. As a broad definition, the goal of alignment is to make a language model's outputs be safe, helpful, and useful to people. This was done through techniques like reinforcement learning from human feedback, where what researchers did is they took a whole bunch of generated outputs and then had humans actually rank which ones they preferred. This preference dataset would then be used to train a secondary model on human preference ranking. Essentially, it would be able to take in a string or strings of text and then accurately provide some sort of feedback on which ones would be preferred more highly. This feedback from the preference ranking model is then what will be used as the reward model for the language model in RLHF and update its policy as such to maximize the reward of creating outputs that would be highly preferred by people. And this was adopted in environments like ChatGPT to train models to generate more useful, desired, safe, and reliable outputs. There were also some advancements with preference training, techniques like process reward models that are able to look not just at the end outcome and score, but the intermediate steps to see which intermediate steps affected the outcome the most to create those desirable results. And other advancements like direct policy optimization were applied to alignment that actually completely forgoes reinforcement learning by training on preference data sets of pairwise examples. So, which of two outputs were preferred by a person. And while alignment and using reinforcement learning for alignment is still alive and well today, more recently, RL has proven also useful when applied to more verifiable tasks, which in this case mean environments where we can clearly define the success of an outcome as either a pass or a fail, something like that. And this was mostly spurred by the release of DeepSeek R1, which showed emergent reasoning capabilities learned in LLMs as a byproduct of reinforcement learning with very simple verifiable tasks. In short, methods like reinforcement learning from human feedback are more oriented towards aligning and refining models' behavior based on subjective human, or in some cases, AI preferences, whereas reinforcement learning with verifiable rewards, or RLVR, focuses on the automatic and objective feedback, like answer correctness, to help models develop procedural capabilities through these stronger verifiable signals. Most immediately, this is where we've seen the trend of actually instilling a reasoning and thinking capability within models come to play, and it was a byproduct of experiments ran with reinforcement learning on verifiable rewards in domains such as math, code gen, and logical proofs. In the case of something like DeepSeek R1, they note this aha moment where, when faced with a math problem, the model over the course of time is encouraged to do some form of thinking to solve the process and actually learns to do some backtracking, reflection, and reasoning along the way. And the novel part of this is that it was completely emergent and wasn't necessarily encouraged by the actual creators of the model, just from the reward signals that the model was getting back as to whether or not something like this math problem was solved correctly. It found that if it generated a little bit more of its thoughts, did more backtracking and double checking, and imitated some reasoning capabilities, it tended to perform better on this task. However, it was not necessarily encouraged to do any of those things. It learned to do that procedure through operating in the environment and getting back the rewards of these verifiable tasks. More succinctly, I note that OpenAI's O series and DeepSeek R1 demonstrate that training language models with these verifiable rewards enables them to learn and generate procedures. So what appears as reasoning in this case is actually more the emergent byproduct of these models learning to construct, execute, and adapt procedural sequences that reliably achieve these verifiable outcomes. And this is a result of reinforcement learning's encouragement of exploration through learning in an environment like this. So by optimizing against these objective verifiable outcomes, as the model tries, fails, and succeeds at multiple different approaches to these tasks, it learns finally to navigate the complex problem spaces, develop specialized capabilities, and improve at long horizon multi-step scenarios. As an added bonus, this can eliminate also a lot of the added overhead of doing things like training reward models or collecting a massive amount of data, like in the case of supervised fine-tuning. Instead, you mostly just need a well-defined environment, as well as the ability to objectively define whether or not the task at hand has been completed or not. And this technique has been applied with a lot of success in a few different areas immediately. We've seen, obviously, the massive advancement in autonomous coding agents. Things like Cursor's Composer, Claude Code, and Codex all use these types of setups where the signal is more end-to-end task success, test coverage from generated code, and successful deployment metrics. Obviously, things like code and mathematics are a very good first step for these kinds of environments, as code and math tend to also have some sort of objective verification as to whether it's right or wrong, deploys or doesn't, compiles or not, things like that. Outside of just code, it's been applied to things like ChatGPT, Claude, Gemini, and other open-ended assistants to assist in following complex multi-step instructions, maintaining conversational consistency in long context scenarios, as well as more complex tool use. And the third example here that we've seen is the introduction of browser and graphical user interface automation. Pretty much everybody's been releasing some form of an AI browser for some reason, but this can definitely be a byproduct of RLVR because agents can then learn to navigate interfaces and complete multi-step workflows on browsers where success is clearly defined. Things like booking a flight, extracting data from a web page, completing a purchase are all incredibly verifiable tasks. But clearly, we've seen RLVR techniques produce emergent capabilities like reasoning behavior, sophisticated tool use, and complex procedural learning. One of the more compelling documentations of this that I've seen is in this paper, Reinforcement Learning for Long Horizon Interactive LLM Agents, that comes out of Apple, where given the environment app world, which actually simulates and tests an agent's ability to interact with a phone or app-like environment, they saw the following procedural learnings despite only using a simple task completion reward, which included things like avoiding open loop control when calling tools, consistently reading API documentation before attempting calls, making fewer assumptions about system states, using fewer placeholder values in API calls, and persisting through API errors rather than giving up. As noted, the great part about this is that the language model learned to do all of these different procedural things just from getting signals about whether or not the task has actually been completed successfully. It wasn't necessarily encouraged or showed specific examples of how to do all of these things. These all came about as emergent learnings from the RLVR process. So you can start to see why a lot of researchers and companies have started to apply these techniques and find great excitement in them. So to give a quick one-liner of what we've been over so far, supervised fine-tuning is the foundation that teaches a language model what to do and how to sound by maximizing imitation of curated behavior. Preference-based reinforcement learning then reshapes that behavior towards subjective desirability, while the final reinforcement learning with verifiable rewards pushes towards objective task success and procedure generalization. With all of that theory in mind, let's switch gears slightly and actually talk about creating our own reinforcement learning environment, defining all of the rewards, and training a language model here, starting of course with the environment. And the environment is the most important part of the reinforcement learning with verifiable rewards loop because it completely encompasses the world in which the language model is going to operate within, defining what actions it can take, the rewards as a result of those actions, and is completely crafted to encourage whatever desired behavior outcomes we want. So if we're doing reinforcement learning with verifiable rewards, a fundamental consideration is then, naturally, verifiability. As mentioned, the strongest environments have these very clear binary signals where we can define whether or not something is correct or incorrect, has passed or failed, or is working or not. And these rewards need to be able to be automatically and objectively determined from the environment. Now, it's possible to use different fuzzy or continuous rewards using things like reward models or other different algorithms, but the beauty in all of this comes from the simplicity of just binary pass-fail, 1 or 0 rewards. I particularly like this quote from Jason Wei, who's a researcher and contributor to OpenAI's O1 and deep research models, where he coins the verifier's rule that the ease of training AI to solve a task is proportional to how verifiable the task is. All tasks that are possible to solve and easy to verify will be solved by AI. So in other words, we can train a model to tackle any kind of complex problem we can think of, as long as we can easily check and verify that their solution is correct. So with that in mind, let's actually find a verifiable task that we can include and create an environment around. The one that I chose actually ended up being the task of PII masking, which essentially I want to teach a language model to redact personally identifiable information, otherwise referred to as PII, from text. I was originally inspired by this when I came across this data set by AI for Privacy of the Open PII Masking 500K dataset that has 500,000 rows of source text and masked text where the PII data has been masked and removed. And this is going to be a perfect task because we have both a clear input, which is the prompt and the original text, as well as a verifiable expected outcome, the redacted transformation. And we can directly check whether or not a piece of text has been successfully redacted by comparing it to our ground truth label within the dataset. It also helps as well that redacting PII information is still complicated enough given occasional subjectivity of the data and the large number of labels that PII can fall into, such as title, name, county, medical professional, etc., etc. So with our task and dataset, I did a little bit of some transformations to simplify things. I took out just the English US examples from the dataset, and I removed all of the individual labels and replaced them all with just PII masks as seen here. I've also counted the number of masks in a dictionary here in the info as metadata. So now a single example looks like this with our question, answer, info, and task here, where the question is going to include the original text. The answer is going to include the redacted text with our PII masks here. Info has, of course, the count, and then the task. Now, this specific format is going to make sense a little bit later when we actually get to the code of this. But in the meantime, I've also uploaded this on Hugging Face, but full props to AI for privacy here for the original data. So with our scenario and a way to verify whether or not it is right or wrong, we can create our reward functions. With reinforcement learning through verifiable rewards, the two primary types of rewards tend to fall into accuracy and format-based rewards. Accuracy rewards, of course, cover the clear pass-fail signals based on objective correctness. For example, things like task completion, mathematical solutions, and code execution. Well, format and structural rewards impose various constraints on how models actually organize their outputs. For example, we see this used in things like including the use of XML think tags, enforcing JSON schemas, function call formats, or different length constraints. And while these two kinds of rewards are, of course, going to be the most important, there is still the possibility of using heuristic proxies or fuzzy signals. By heuristic proxies, we more so mean lightweight signals that correlate with quality without having that direct ground truth. Things like tool usage efficiency, which would reward minimal API calls or optimal tool selection, response coherence, things like character token length ratios, presence of required sections. We can do things like partial matching, giving credit for solutions that are partially correct, or different performance metrics, speed of solution, computational efficiency. These don't directly measure yes or no whether or not something is well, but can give or correlate with some different quality metrics. And of course, we can still have different rewards based on generative models themselves. This is where forms of language models as a judge are often implemented, where human-like judgment is needed, but human feedback is not necessarily scalable. We see things like using strong language models to assess response quality, which can also produce nuanced text feedback along with scalar rewards, or mapping that text feedback to some sort of scale to provide a single reward. But, while useful, I note here that it's best to start with straightforward accuracy and format rewards before turning to these more complicated other reinforcement learning rewards setups. Of course, the beauty of reinforcement learning with verifiable rewards is that we don't necessarily need all of the heuristic or fuzzy rewards. We can just have straightforward accuracy and format and still get those emergent procedural benefits. So for our environment and for our PII masking scenario, I am going to define 3 specific rewards: one accuracy, one format, and just for a little bit of fun, a partial heuristic signal. The accuracy reward is going to be a simple binary check if the model generated text is equal to the expected masked output. A format reward is going to be a check if the model generates its response within some expected XML tags. I'm going to instruct the model to put its output within a masked underscore output tag here. And then my partial heuristic signal is going to be a check of whether the count of PII masks actually equals the expected count. In terms of importance, however, accuracy is, of course, the most important, and then format is going to follow second in the context of RLVR. So, with the ideas behind our environment and rewards out there and our dataset ready to go, what we can do is actually start implementing this. And to do that, I am going to be using the verifiers library. Verifiers itself is essentially a robust tool set that allows people to create, use, and share reinforcement learning environments that are focused around language model training and evaluation. And a big shout out to Will Brown here for putting together the original Verifiers library, which has further been commercialized via Prime Intellect here that supports the whole operation. So if you do find yourself making an environment like I have here, go ahead and give them a star on GitHub. They truly deserve it. So before we break down the individual parts of this, our fully constructed environment is going to look a little bit like this as defined in a load environment function. So we'll have a system prompt, a dataset loading section, a parser section, a rewards function section, a rubric, and then that'll all be packaged up nicely together into a environment. In our case, we're going to be using what's called a singleton environment, which is best used if you have a clear input and output and don't need multiple specific steps towards getting that task completion. However, if you want to view all of the other different kinds of environments and things that Verifier supports, I recommend you check out the docs. They've got good documentation here. But to briefly go over the various sections, our dataset is going to be loaded via Hugging Face datasets so that it'll pull directly from the Hugging Face hub. We load the only split of it, which is going to be the train split here, and then do a little bit of selection logic if that variable has been passed through. If not, it'll of course just select the entire data set. Then we do some splitting into a train and eval set, which by default is just going to grab 20% of the shuffled data set and split it out into a train and test here. Now, Verifier's data loader expects a dataset to be in the format of question, answer, info, and task here, which is why my dataset that I've uploaded to the hub is in this specific format. Now, instead of just including a string in a question column here, you can also put in a list of chat completion messages by just changing this column to prompt. However, if you do have a question column, what you can instead do is provide a system prompt, and the Verifiers library will automatically create the chat completion formatted messages with a system prompt and then a user question. So in our case, since we're using the question trick here and Verifier's data loading, we are going to provide a system prompt, which is very simply just replace all personally identifiable information, PII, in the text with PII tags. PII includes a couple of these examples of identifying information. I have two specific examples here, and then my instructions are to return only the masked text wrapped in masked output XML tags, and then a quick format example here. So this is all going to be combined together with every single example from the data set and passed through for the model to do its generation. But once the model does generate something, we need a way to actually parse out the generated output so that we can compare it then to our expected output and pass that all through to our reward functions. So in other words, we need a parser. Now, Verifiers has a couple built-in parsers, which we are going to use. The specific one being the XML parser, which is pretty much defined in the name. You pass it some fields of what is going to be expected in the generated text that the model is going to generate, as well as which one is the specific answer field, and it returns a result that you can dot into with the specific tags. We have a pretty simple scenario with just the masked output XML tags expected. So we are going to pass in one field, masked output, and that is also going to be the answer field. And now we have our parser. Lovely. And last but not least, before we package everything together, we need to define our reward functions. For our accuracy reward, we're going to be using a very simple exact match reward that will take in the parser, the completion generated from the language model, and the answer. And we are going to compare whether the answer is equal to the ground truth answer and return a 1 if so, and a 0 if not. For our format reward, the cool thing about verifiers is that we can use whatever parser we defined that is built in to also get a format reward function. So by calling the get format reward function, it returns back a format reward function that follows the following logic. Field presence counts for 40%, essentially is the masked output tag present. Correct spacing is 20%, does it parse correctly with proper spacing. Starting with the first field is another 20%, and ending with the last field is another 20%. So if all goes well, our final answer and format should have simply just the masked output here with the final answer in between them. For our more for fun heuristic signal here, where we are counting the number of PII labels, we are going to parse our completion, get the count of PII count from our info metadata where it's captured in our data set, count the occurrences of the PII mask in the completion's answer, and then return 1 if it is equal to the expected count, else 0. So with our 3 defined reward signals, we can put these all together into a verifier's rubric, where we're going to pass in our parser, the 3 functions, and then a specific weighting. So we can actually add in and affect how important each one of these functions actually is to the final reward at the end. I put in a weighting of 1.0 for the exact match, 0.5 for the count reward, and then 0.1 for the format reward. So this yields a composite score in the range of 0 to 1.6, where exact match correctness dominates up to a full 1.0, with a couple smaller bonuses for correct PII counting and well-formatted output. So intuitively, as I've been mentioning, getting an exact match is what matters most in the training of this, with some light auxiliary credit from our PII count and formatting. And now with everything defined, we can package it up nicely into our singleton environment, which in the full function is simply returned. And the cool part about the verifiers package, as well as Prime Intellect, who is supporting the package fully, is that they have created an open source environments hub. This allows you to take your RL environments and publish them in a way that others can actually see the code and use them in their own situations. So I have naturally gone ahead and taken this environment and uploaded it here. So you can take a look here and use this with any sort of integration that Prime Intellect offers, as well as any of the benefits of the verifiers package itself. So now that we have our full environment, the last thing we need to do is actually use it and train a model. And for this, I decided to use and had the privilege of beta testing Tinker. This is Thinking Machine Labs API for actually training models, where you essentially create the training loop and pass in the data, and they handle all of the backend training infrastructure. The great part about Tinker, on top of all of its already proposed benefits, is that they support reinforcement learning naturally within their environment here, and even have some scripts and predefined documentation on how to integrate Tinker with verifiers itself. And these recipes here have been, of course, created by Will Brown once again, so shout out to him again for providing this lovely integration example. If you're interested in the nitty-gritty of actually creating the training scripts here, I recommend you definitely check out some of the files behind the scenes, like this train.py, and you can see exactly what's going on. But for our case, I kicked off that training recipe with the following arguments here. Notably, I opted to train Qwen3 4B Instruct 2507, which is a little bit of a mouthful, but it is a nice lightweight 4 billion parameter model, so very easy to deploy in situations where you would need massive inference, such as masking a large amount of PII data. Not to mention that it's also cheaper to train, smaller and faster, and all of those benefits too. Actually doing that looks a little bit like this, where when passing in that script, with of course a more limited number of training examples here, we will see everything get kicked off in the Tinker backend. So it's going to create a training client and then start to perform the rollouts and evaluations and then wait updates. So there you go. You can start to see all of the generated output here, and then we can see the actual trajectory metrics of our exact match, PII count, format reward function, and it will go through and log everything nicely. Running this produced the lovely looking loss curve here, where we can see over the course of a total of 740 steps, which came out of our 30,000 examples, we go from an average of roughly 0.8 in our cumulative reward up to almost around 1.1-ish, 1.15. But we can see a clear positive trend as the model learns from its explorations and gets better at this task. Now, Tinker outputs LoRa adapters as its final training artifact. So what I did is, after all of this training, I downloaded that adapter, merged it with the base model, and that has become this model here, the Instruct 2507 PII RL model, which has been uploaded to Hugging Face with some instructions on how to actually use this if you wish. Now, to verify whether or not our training actually did anything, I ran some evaluations within my environment using a few separate models, and we see our trained model here coming up at the top. With given 50 examples and 3 rollouts per example, we see an average reward of 0.89. This clearly beats out Claude Sonnet at 0.72, GPT-5 at 0.68, the base Instruct model Qwen34B at 0.63, and GPT-5 Nano at 0.557 here. Now, naturally, further evaluations on held out data and more comprehensive evaluations would have to be run to truly say that this is truly improving, but it is good to see. And I think with that, combined with a little bit of our reward curve here, we can say that our model has learned a thing or two. Now, with all of that theory and experience under our belt, let's talk a little bit about what the takeaways of this is. First off, reinforcement learning really has continued to be a critical step in language model post-training, complementing a lot of what supervised fine-tuning has already offered us by enabling preference training through techniques like reinforcement learning through human feedback and the generalization of procedures through reinforcement learning with verifiable rewards. The field of reinforcement learning with verifiable rewards has become notably popular, mostly due to its simplicity and implementation, the limited amount of data that you actually need to get benefits, as well as all of the emergent things that come up, such as what we highlighted with reasoning in DeepSeek or different procedural understandings and learnings with the Apple research. It's super interesting to see that we can teach language models how to do things, and then it can generalize that across unseen examples of how to do the same thing in similar environments. In the lifecycle of post-training of language models, a general rule is that supervised fine-tuning teaches the what, our formats, facts, and behaviors. Preference training teaches the how well, quality, style, and safety, and then reinforcement learning with verifiable rewards teaches the how-to, procedures, strategies, and problem solving. This was all kicked off by the emergent reasoning capabilities in models like DeepSeek R1 that were byproducts of optimizing for these verifiable outcomes, not just explicitly training on these different behaviors. The models themselves actually learned to construct and execute procedures that reliably achieved those expected verifiable results. When actually implementing reinforcement learning with verifiable rewards, we know that the environment is one of the most important things here, defining the world, action space, and all of the reward signals. Rewards themselves then tend to focus on our binary indicators of accuracy and format on the output, often scoring the full sequence rather than the individual segments or intermediate steps. Through all this, reinforcement learning through verifiable rewards has proved to be an exciting and promising direction for developing language models with specialized capabilities, and the key here is the verifiability itself. If you can programmatically check whether or not a task has actually been completed successfully, it is highly likely that you can train a model to excel at it through reinforcement learning. So now, with all of this being said, I hope you understand a thing or two about reinforcement learning, how it's applied to language models, and how you can start to use some of the more modern techniques like RLVR within your own day-to-day. If you do, definitely share what you've got in the comments below on the Verifiers Hub, publish some models to Hugging Face, and contribute to the open source system as a whole. And if you liked the video, make sure to like the video. If you have any questions or comments, leave them in the comments below. And if you want to see more like this, consider subscribing. Thank you and have a great day.